Hi everyone, and welcome back to the series of Electrical B7 Power Systems Engineering. This basically a recent PEO question. It's about symmetrical and unsymmetrical faults. I solved the first part where we found the per unit impedances for positive, negative, and zero sequence circuits. Now, in part two, we will be using the information that we have gained from the part one in solving this part and the coming part as well. So that it will be part three of this question. So here it says that for the power system of part one, so it means that the question that we solved, which is part one, calculate the fault current in TX1. So we want to see if a fault happened where a three-phase to ground, so a symmetrical fault happened, and the middle of the transmission. So if I have a fault happened here in the middle, okay, so this is my fault current. I want to know how much of this fault current will go from this side from the transformer 1. And this is basically a question about the symmetrical fault. When we have a three-phase to ground, we call it symmetrical faults. And the result for that, the system stayed balanced. And we work on a single-phase circuit. And we work only on the positive sequence. Because if the system is balanced, there is no zero sequence or negative sequence components, and we only have the positive sequence. So for example, here, this is a system of two generators connected to two transformers, two transmission lines, and the fault happened here. Now, when we analyze the system, we convert the single line diagram to a reactance diagram in per unit. And basically, then we do the calculations as we will basically see. But as you can see here, I have used only the positive sequence. And how do I know it's the positive sequence circuit? As I mentioned in the previous video, the positive sequence is the only sequence that will have a voltage source. The negative sequence and the zero sequence, they are just reactances. There is no any voltage source there. So let's go to the question. Okay, so here we have this system. So we need to basically draw the impedance diagram, the same one we did before, which is the positive sequence. So I will not derive it here because I derived it in part one. So basically here we'll have and I will use the common per unit system, which is the 100 MVA and 230 kilovolt at the transmission line. So we came up with this. So basically here we have the EG1 and EG2, and the fault happened at the middle of the transmission line. So this is basically the impedance of the generator, which is 1.736. This is 0.233. The impedance of the transmission line is 0.189. Now, since the fault happened at the middle, so one half of the transmission line impedance will be to the left side and the other half to the right side. So I will have here 0.189 divided by 2, and here also 0.189 divided by 2, then 0.175 for the TX2, and then we will have 1.975 for generator 2. So that is basically the reactance diagram. Now, as I mentioned in previous questions about symmetrical faults, we need to find the impedance between the fault point to the ground. And to find the Thevenin equivalent for this, we short circuit the sources. So this source is short circuited and this is short circuit. So we need to find X Thevenin. And clearly you can see here, it is this branch in parallel with this branch. So basically it is the 0.0945, which is the 0.189 over 2 plus 0.233 plus 1.736. So all of this in series in parallel with 0.0945 plus 0.175 plus 1.975. So these two are in parallel. When you add this would be equal to 2.0635, and this would be 2.2445. So your x Thevenin is equal to 2.0635 times 2.2445, because they are in parallel, divide by their summation, 2.0635 plus 2.2445, and this will give me a total x Thevenin equal to 1.075 per unit. So this is your x Thevenin. Okay, so this is the first thing. You find the x Thevenin between the fault point to the common ground of the whole power system. Now, once I know x Thevenin, okay, so let me draw this one here just to imagine what is going on here. So here I can find the fault current. So the fault current IF, we always assume that the voltages before the fault was one angle of 0 divided by 1.075, and this is equal to 0.93 per unit. Now, this is the total fault current that happened at the middle to the transmission line. But that's not what we want. We want to know the fault current that go through here. So we will have here part of the fault current coming from this side and part of this fault current coming from the other side. So these two generators will contribute to the fault current to find the total value. Now, how to can find IF1? Very simple current division. So multiply 0.93 times the impedance of this branch, which is the 2.2445, divided by the summation of the impedance of the left and the right branch, 2.2445 plus 2.0635, and this will give us 0.485 per unit. This is what is coming from the others, this side, from the transformer 1. From transformer 2, you will have the 0.93 minus the 0.485. That would be the contribution from the other side. So this is how we deal with a symmetrical fault. In next video, I will try to cover when we have unsymmetrical faults, how we can handle such question.